Hello, my name is Katra Mayumi Godoy, and today we will be going over optical responses in materials. Specifically, we're going to look at nonlinear optics. So before we even get into that, let's get into what is an optical response in a material in more broader terms. So in general, that is just how a material interacts with light. So these are some common examples of its applications that I included here. That includes fiber optics, frequency conversion, optical communication and switching, medical imaging, and quantum information. So first, we're going to go over the differences between linear and nonlinear optics just to put things into perspective before we dive into nonlinear optics, or NLO for short. So first, let's go over linear optics. So this just looks at how light interacts with matter at low intensities. So this is a key distinction. It typically involves only one photon per atom or molecule. So this fundamental principle is that the material's response is directly proportional to the input light intensity. This is another key difference. So it satisfies this principle called, principle of superposition. So what does that mean? Or what even is that? So that is just the total response to multiple waves is just the sum of the individual responses. So in linear optics, there is no creation of new frequencies, another key distinction. And what does that look like? The light passing through retains its original frequency. And so now we're going to look at the equation for linear optics and define its terms. So P is polarization, this funny looking E is epsilon zero, and that represents the vacuum permittivity. X1 is really chi1, it is a Greek symbol, and that represents linear susceptibility, and E is the electric field. So now we're going to compare this to nonlinear optics. So this requires high intensity light. That is a key difference that we were talking about. At this extreme intensity, multiple photons interact with the material at the same time. So this response is nonlinear, and it means that the output is disproportionate. In other words, the output is not directly proportional to the input strength like in linear optics. And so this allows for interactions between different light frequencies and results in frequency mixing, and the end result is the creation of new frequencies like we were talking about. And so this example includes harmonic generation. So I included an image here just to show the comparison between the two. An example for nonlinear optics is that, let's say you have a red light and it enters a material. There is a possibility it could be converted to green light. So that is just an example. So the linear approximation fails because the high optical fields disrupt the field strengths of the atoms. The core mechanism relies on how intense light interacts with charges. So matter is made up of charges. So when light, which has an electric field E, interacts with matter, it creates what is called a separation of these charges. So this charge separation results in what is called induced dipole moments. That is the image you're looking at here. So the induced electric polarization P is defined as the net average dipole moment per volume. In linear optics, polarization P is simply proportional to E. But for nonlinear optics, or at high optical fields, that is not the case. The relationship between P and E is nonlinear. So instead, the polarization is written as power expansion involving coefficients multiplied by higher orders of the electric field. And that is essentially the equation that you see on the top right here. So the Greek chi symbols, xn, or chi n, are the optical susceptibilities which quantify the material's response. Chi1 is a linear optical susceptibility that we saw for linear optics. So we're now going to compare Chi2 and Chi3. So these are higher order terms. Chi2 is a second order and Chi3 is a third order, and so on and so forth. So we'll call those Chi-n. And these are all nonlinear responses, and they are terms that are responsible for the presence of new frequency components. So the symmetry of the material dictates which terms exist. A contribution from Chi2 only happens if there is a non-centrosymmetric media. That is not the case for Chi3. For Chi3, it can happen with any medium regardless of symmetry. So this includes isotropic materials that are gases, liquids, and gases, or glasses. So a famous example of second-order nonlinearity is second harmonic generation, or SHG. In SHG, two incident photons of frequency called omega combine to create a single output photon with twice the frequency, 2 times omega. So the experimental observation of SHG in 1961 marked the birth of nonlinear optics. So what happened in this research? They sent a light from a ruby razor that had a frequency of omega through a quartz crystal. And so the emergent light was observed in the ultraviolet region, and it had a frequency of 2 times omega. So a lot of these second order processes involve the interaction of three fields where energy is conserved. So this means that the sum of two lower frequencies equal the highest frequency, omega 3. So omega 3 equals omega 1 plus omega 2. For efficient energy transfer, a crucial requirement is the phase matching condition. The wave vectors must also be balanced. That is what that means. And it also means that there is some sort of momentum conservation requirement. Other important Qi2 processes are related to parametric amplification and oscillation. So in parametric amplification, there's an intense high-frequency pump beam, omega 3, and that is used to amplify a lower frequency signal beam, omega 2. And it simultaneously generates an either field called omega 1. So this Manley-Rao relation governs this. For each pump photon subtracted, one single photon and one single either photon are created. So placing mirrors around nonlinear medium create what is called an optical parametric oscillator, or OPO for short. And these are widely used as coherent tunable light sources. There we go. So since Qi3 is present in all media, it governs common nonlinear optic phenomenon. Third harmonic generation occurs when three incident photons of frequency omega result in a photon with triple the frequency, 3 times omega. A major third-order effect is intensity-dependent refractive index. This is also known as optical Kerr effect. And what does that mean? It just means that the refractive index N of a material is dependent on the light intensity, I, of the light used to measure it. The intensity dependence leads to a phenomenon like self-phase modulation, or SPM for short. And this is where phase shift experienced by short pulse causes it to spectrally broaden. This can also cause self-focusing and self-defocusing. So let's say if the nonlinear refractive index, N2, is positive, the medium acts like a positive lens, and this focuses the light intensely. Excuse me. When this self-focusing tendency precisely compensates for the natural spreading or diffraction of a beam, a phenomenon called self-trapping can occur. So this leads to the formation of what is called spatial solitons. And these are stationary, stable solutions that hold their shape. Other Qi3 processes involved complex light matter energy transfers, like two-photon absorption, or TPA, and this is a simultaneous absorption of two photons, hence the name, which moves an electron from the ground state to a higher state via a virtual state. So, excited state absorption, or ESA, is if the input intensity is strong enough to deplete the ground state, and this then produces different behaviors. These include saturable absorption, SA, or reverse saturable absorption, or RSA. So saturable absorption is when the transmission, saturable absorption enhances transmission change, and RSA decreases this transmission. You can see these relations presented in this equation. Transmission increases when sigma E is less than sigma G. Transmission for RSA decreases when sigma E is greater than sigma G. So, stimulated scattering includes stimulated Raman scattering and stimulated Brillouin scattering. These are governed by the third order nonlinearity, or Qi3. So stimulated Raman scattering is the vibrational energy exchange, whereas SBS is the acoustic phonon scattering. So that was a lot of information, but hopefully what you have gathered from all of these concepts is that nonlinear optics has a lot of applications. I included some examples here in the slide: telecommunications, biomedical imaging, and microscopy, defense and sensing, and essentially all of these applications allow nonlinear optics to continue to push the boundaries of photonic technology. And by understanding how these matter respond nonlinearly to intense light, scientists are able to master the ability to control light using light. And this opens the door to countless future photonic innovations. Thank you for your time. I hope you learned something, and happy holidays.